Like any other initiative, we cannot know the true effectiveness of TPM without having a means of measuring our performance. Let's examine some of these measures. OEE, or Overall Equipment Effectiveness, is the primary metric in TPM. OEE is the product of availability, performance efficiency, and speed rate at which quality products are produced. Availability is the ratio of loading time less downtime divided by loading time. Recognize that downtime shown in this calculation is unplanned downtime. Loading time also includes downtime, but this is planned downtime. To find the true loading time, we must subtract any planned downtime. Planned downtime would be things like scheduled maintenance and production meetings. Let's consider this example. Time frames are given for the total time for the shift, setup, planned downtime, and unplanned downtime. We wish to find the loading time and the availability. The loading time is 460 minutes. The availability is the operating time divided by the loading time, or 85.7%. Now let's extend the previous example a little further. The theoretical and actual cycle times and process amount are offered here. We also know that 97% of all products produced meet quality standards. Let's find the performance efficiency, the rate, and the OEE. Operating speed rate is the ratio of theoretical to actual cycle time, or 60%. Net operating rate is the process amount multiplied by the actual cycle time divided by the operating time, or 82.3%. Performance efficiency is the product of the operating speed rate and the net operating rate, or 49.4%. Overall equipment effectiveness is the product of availability, PE, and the rate of quality products, or 41.1%. This is actually a very low OEE. Companies that have highly mastered the principles of TPM perform at OEEs of at least 85%. Because the OEE calculation consists of 3 efficiencies in series, this leaves very little room for error. Even aiming for availability, PE, and quality rate at or near 95%, we barely deliver a TPM process at 85%. There are varying paths to the implementation of a successful TPM program. Here are some useful steps to follow. We should begin by orienting the organization to TPM. An organization can best be aligned with the aims of a new initiative when it is formally introduced, explained, and aligned with the imperatives of the business. This alignment should also occur within functional areas of the organization. TPM can benefit every level of the organization. Each member should understand what they can gain from active participation and commitment to TPM. TPM policies and objectives should be established, documented, and communicated regularly. If an organization sees TPM as a potential solution, it likely already knows of critical processes where TPM could help improve OEE and availability. Use dedicated teams of individuals to investigate the process and outline measures to move closer to an ideal state of TPM. As part of this investigation, items considered to be autonomous maintenance and scheduled maintenance should be categorized and grouped. Autonomous maintenance programs are deployed at the operator level, whereas scheduled maintenance programs are kept within the maintenance group's wheelhouse. All employees involved in TPM should be formally trained so that everyone understands their role and responsibility. Moving forward, as new equipment is introduced and existing equipment is changed or maintained, a series of protocols should be established for the installation, operation, and validation of equipment. The core of effective TPM lies in the dedication of autonomous maintenance activities. These efforts are left in the hands of self-directed workforces. The workforce will develop the activities, ensure the completion of these activities, problem solve when needed, and track their own performance. One way to effectively demonstrate that goals are being monitored, maintained, and achieved is through the use of visual controls. Visual controls can take the form of production boards, schedule boards, tool boards, Kanban, and Jidoka. Jidoka is a device that stops a machine whenever a defective product is produced. It is a form of automation with human dependencies. Without the need for reports and formal exchange of information, visual control systems create a continual and instantaneous means from which management, supervision, and operators can obtain a visual assessment of the state of the process. When utilized with care and resolution, visual control systems can be therapeutic and convey a sense of stability. A factory that embraces visual control systems emphasizes the display of performance and goals. Operators use these visual cues to drive improvement, reduce waste, and eliminate errors.